All right, welcome to lesson 10.4. We're going to be talking about harmonic series, P series, and the comparison tests, for convergence. I hope that you're doing okay at home. Please make sure you email me or text me or call me if you're having any trouble, you're not understanding something, you need support. Please reach out. I want to help out as best I can, but I need you to communicate with me about that, all right? So, let's go ahead and get started. Last lesson, if you recall, I brought up two different series that I said we would return to, and we're going to return to them now. So let's talk about them a little more. One of the series was right here. This series, the sum from 1 to infinity of 1 over n. The other series was the series summed from 1 to, or the sequence summed from 1 to 100 of 1 over n squared. Both of these are what we refer to as P series. Okay? A P series has the form 1 to infinity of 1 over n to the p, where p is a real number. That's the only requirement there. 1 over n to the p, where p is some real number, okay? And it turns out that there are some special rules to remember around P series. And P series themselves kind of pose a very small subset of the overall series world, but a very important subset because they're actually quite easy to sort of deal with. They have a very simple rule for convergence, and so we actually like to use P series a lot when discussing convergence because they represent a really simple series to compare other series to because they are so sort of simple in there. All right? Give me a moment. Okay. So, when we're talking about P series, the one main rule, the one main thing we need to remember that is important about convergence for P series is that P series converge, oh my goodness, in the half a second here I have lost my pen, there it is, that P series converge if our value of P is greater than 1. That's the only rule about convergence we need to know, actually, that P series converge if the value of P is greater than 1. All right? And this makes things actually really simple. As long as we remember that rule as we're dealing with different power series, then we are actually in pretty good shape, as long as we can get our mind thinking about how or whether or not the P value is greater than 1. Okay? So, this is actually a really big thing to kind of understand in terms of importance. Basically, we know that any series of this form converges if P is greater than 1. Not greater than or equal to 1, but greater than 1. If it's equal to 1, we end up with this series here, which we saw through the integral test that you could check, is divergent. But if P is greater than 1, like so, the series converges, and you can use the integral test to show that. There's actually been a lot of work on these P series from like a long time ago. Determining the value of that a P series converges to is actually quite difficult, but I think it's fascinating. Maybe you will. I'm hoping so. Steven is probably smiling. The sum of 1 to infinity, from 1 to infinity of 1 over n squared is actually pi squared over 6. Isn't that crazy? It's such like an interesting number with one of our famous irrationals, and that this series sums to pi squared over 6. We won't prove that, but if you get into lots of series stuff, you can explore the wonderful world of what they sum to. So for harmonic series, this special series, P series, where P is 1, is called the harmonic series. This series is really then the kind of border of divergence. We call this series, like I said, the harmonic series. It's actually an incredibly interesting series in its own right. You can go and explore a lot of stuff about it. But for example, its name comes from, if you might imagine, from, oh man, lots of typos today, from the ideas of musical overtones, or the idea of musical overtones, or harmonics. And the wavelengths of overtones on a vibrating string are half, 1/3, 1/4, 1/5, etc. of that string's fundamental wavelength, and so we call it the harmonic series. Because the series goes 1/1, 1/2, 1/3, 1/4, and so on. The harmonic series we can sort of visually represent like this, that our first, if we drew a rectangle with a height of 1/x or 1/n, the first one would be 1, then half, then 1/3, then 1/4, then 1/5. If we sum all those up, it will diverge. It will diverge. All right. But what about a slightly altered form of this harmonic series? The series from 1 to infinity of -1 to the n+1/n. So it's basically our harmonic series, except that it has an alternating term that's going to make the sign flip. We call this the alternating harmonic series. It is a harmonic series, but with an alternating factor back and forth. All right. So for example, it goes 1/1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. But what's fascinating and important to remember, it seems like a rather trivial thing, but at least when it comes to AP tests, like this is something that has come up before, and we can use a different test later on to prove this. But this alternating harmonic series, just file it away, this alternating harmonic series converges to natural log of 2. So 1/n is our harmonic series, diverges. The alternating harmonic series, if we have some series that is harmonic but alternating, it doesn't exactly have to look exactly like this, but an alternating harmonic series actually converges, and this specific one converges to the natural log of 2. Isn't that crazy? Another relatively round number in the grand scheme of things in terms of ease of writing and expressing. I just think this is fascinating. We don't have time to explore this now, but if you want to, there's lots of great resources you can look to see why, and we'll explore a test later on to prove this convergence. But you can even tell graphically that if you actually do sum by sum, you see that the series down here kind of oscillates back and forth across 0 from positive to negative. And essentially what happens is they end up balancing out. The actual accumulated sum ends up converging to natural log of 2. Interesting, right? All right, big things here. We have a p-series. P-series converge if p is greater than 1. They have the structure 1/n to the p. Our harmonic series, when p is 1, diverges, okay? Important, diverges, harmonic series diverges, but the alternating harmonic series converges. All right, let's put some of this into practice, okay? Some examples. Using p-series to test stuff is relatively straightforward if we can get things to look like what we want, but I'm not guaranteeing all of these use the p-series kind of test. We've looked at different kinds of convergence already, so let's take a look. Determine whether each series diverges or converges. We have 1/n to the pi. This does look like a p-series. Remember, we want to, for p-series stuff, if we can recognize something as 1/n to the p, get something in this form, this is going to indicate to us we want to use p-series ideas, and we're looking for p to be greater than 1, means convergence. Okay. 1/n to the pi. All right. This looks like our p-series format, and pi is greater than 1. So the series, that should say converges. We can say, we don't really call this a test because it is a p-series. Okay. All right, we have n to the negative 1/4. We want to try to get things to look like 1 over n to the p. So let me rewrite this sum as 1 over n to the 1/4. And we can tell that 1/4 is less than or equal to 1. So our series diverges because it is a p series. Notice I stated what's going on with my p-value here and then made my conclusion. Okay. Oh my gosh, I accidentally retyped a thing here. That wasn't supposed to happen. Let's scratch that one. We already did one like that. All right, we can take a look. Okay, interesting. We got a sum down here. It kind of looks like a p-series, but we got this extra kind of term floating around. Let's go ahead and take care of that. So this sum is going to be equal to the sum from n equals 1 to infinity of, if I applied this 5 in there, that'd be 1 over square root of n, right, is 1 n to the half power. I'm going to apply to 5 to it. Power to a power we multiply, so that's n to the 5 halves power, and I can say 5 halves is greater than 1, so my series converges because it is a p series. If you want to strengthen this, you can say because it's a p series with p greater than 1. All right, let's take a look. 2 over n times the 5th root of n. Interesting, we want to try to get into this p-series format, so we can say, okay, n equals 1 to infinity. It looks like we can't get in the p-series format, so we'll call this 2 over, that'd be n times n to the 1/5. I want to try to combine my exponents, so this is going to be the sum from n equals 1 to infinity of 2 over n to the 1st power times n to the 5th power is going to be n to the 6/5 power. All right. And notice all we got here is a factor that's going to multiply it. And so without that factor, we'd have 1 over n to the 6/5. 6/5 is greater than 1. So with the factor, so if 1 over n converges, 1 over n to the 6/5 converges, if we're just multiplying whatever that convergent value is by 2 every time, it will converge also. And so we'll say that this series also converges because 6/5 is greater than 1. So our series converges because it is a p series. We'll do a little more exploring later on with some other tests that we can use to show this kind of thing, but for now, this will suffice. All right, 1 over 5 to the n. Wait a minute. For my p series, I want it to be n to the number. This is number to the n. But we've seen stuff like this. It is geometric. All right, this is a geometric series, so I have other tests I can use for geometric series. What is my main test? As long as I can show this geometric series has an absolute value of r, that is less than 1, the series will converge. So looks like 1 over 5 to the n, we're going to be multiplying by 1/5 each time. 1/5, absolute value of 1/5 is less than 1. So the series converges because it is geometric, not a p-series, but geometric from a few days ago, with absolute value of r less than 1. Okay. Interesting here. We have 1 over j squared plus j. Again, we'll get another test to make this a little stronger here later today. But for now, we can already kind of begin sort of our thinking here. Okay, well, if I'm looking for a power series, a p series, not power, to be 1 over n to the p, this kind of looks like 1 over n to the p, but I got this extra j thing here, right? Okay, if I do a little bit of thinking, well, 1 over j squared, in that case, p would be greater than 1, so it would converge. And all I'm doing is adding some other number to the denominator. So that's going to make these numbers that I'm summing even smaller. So if 1 over j squared converges, 1 over j squared plus j, because adding more to the denominator will make each of the terms smaller, that's going to definitely converge, because 1 over j squared already converges, so I'm making that number even smaller. So it'll converge. All right? We'll have another name for this kind of test that I just kind of did very quickly. But for now, we can compare. We can say that 1 over j squared, we can say 1 over j squared does converge. What I'm going to use right now, just to tease it, converges. I want to say by comparison to 1 over j squared, that sum, which is a p-series that converges with p greater than 1. All right, we'll return to this idea later on. All right, and we have one here. Let's see, n equals 2 to infinity of -1 to the n over n. This looks like the harmonic series, but we have an alternating factor. So I will say that this converges, and all I have to say is because it is the alternating harmonic series. Again, later on we'll have a stronger way of talking about this. For now, we're just kind of building our foundations and our intuition, because it is the alternating harmonic series. All right? So the two problems down here at the bottom that I want you to try, pause the video, and I want you to give these a shot, okay? All right, let's take a look. We want to know which of the following series here converge. So I know that this series here, if I want to try to, it looks like it could be a p-series kind of thing. Now this is equivalent to 1 over n to the 1/3. Yep, looks like a p-series thing, and it will diverge. If I was asked why, diverge, why? Because p is less than or equal to 1. All right? P is less than or equal to 1. So that one's out. All right. 1 to infinity of 3 over pi to the n. That's not a p-series thing. Looks geometric because I have some factor to the n power. Let's see, 3, the absolute value of 3 over pi, if I try to find that r value, is, let's see, 3 divided by 3.14 is less than 1, so it converges. If you're asking about why, because it's a geometric series, and the absolute value of r is less than 1, so it converges. So this guy's okay. Got something interesting here. We got n's to the power, so let me see if I can combine those together to get some sort of p-series thing. So let's see, this would be 1 over n to the 3/5 times n to the half. When I move it down there, I gotta try to combine these two, so I need a common denominator. So the common denominator will be 10. So I'm going to say that this is equal to the sum n equals 1 to infinity of 1 over, let's see, that'd be, here this would be 6/10 plus 5/10 gives me n to the 11/10. So now it looks like a p-series. It's n to the p. So this will converge. If you want to know why, we can say it is a p-series with p being greater than 1. All right. So 1 does not work, but 2 and 3 both converge. Oh my gosh, that should say 2 and 3 right there. All right. I'll be sure to alter these on the actual PDF so that you you don't have the same mistakes that I'm looking at. All right, C, there we go. All right, which of the following series converge? Same kind of question, different series we're looking at. All right. Interesting. This first one is kind of a little different. Again, we'll have some stronger ways to talk about this, but even intuition can help. 1 to infinity, cosine of n, no matter what I go, is going to be stuck between -1 and 1, and we're taking the absolute value of that. So really, this numerator is between 0 and 1. So it's stuck between 0 and 1. And then n cubed, that is a lot like a power series, 1 over n to the 3. If 1 over n to the 3... 1 over n to the 3 converges, then we can imagine then that cosine of n, the absolute value of that, divided by n cubed will also converge. So we'll say, for now, by comparison, excuse me, by comparison to 1 over n cubed, this will converge. Again, we're kind of just using intuition here for some of these, and we'll get stronger ways later on. Cosine of n, again, stays sort of limited. We're dividing it by n cubed, which will converge. So we can imagine that this whole thing will converge. All right, interesting here. We have an alternating term up top. We have n to the 1/3 down here. And we can imagine also, based off of what we know about the alternating harmonic series that converge, that this one will as well. Sure, it doesn't shrink as fast, but it will converge also, and we'll have a test for that later on. Okay? Here, then this converges, and we can kind of think of it by comparison to alternating harmonic series. And if you're sitting there thinking, I don't have like Markwalter, like I would like to know these tests now, we will get to them. I want us to just take the time to sort of process and start to use sort of our instinct about how things compare before we get to comparison tests and other things as well. Okay? All right. 7 over n, this looks like the harmonic series, but we're multiplying it by some factor. Okay, the harmonic series diverges, so we can imagine that this one, when multiplied by a factor, also diverges. So the two that converge here and here. All right, I'm going to go with B. Again, I'll change the answers here to make the PDF match, okay? All right. Let's take a look at an actual convergence test that could help us with some of those that I'm sort of waving my hands over. Okay. Our knowledge of p-series, as I've already kind of teased, really only applies to a narrow number of series. But with the stuff I've already mentioned about comparing to other things, our understanding of p-series is actually really useful for applying to, or for application to, other tests that we might use for convergence. So let's look at 2 today. All right. Let's let there be some sum of terms we're calling a sub n, and it's a series with no negative terms. Okay. If that series has no negative terms, then the series converges if there is a convergent series, we're going to call it Cn for convergent, where a sub n is less than or equal to c sub n. For all n is less than n, where this big N can be infinity or something like that for some integer, or it could be nearing infinity for some integer n. All right, so here's what we got to kind of think about that one. Okay, so this sum will converge if the individual terms are always less than or equal to some other series terms, and that series converges. So we're comparing it to a convergent series, and as long as the terms of our series are less than the terms of that one, then our series has to converge. That makes sense because the terms are smaller. Similarly, if you're looking at some series and it will diverge, if you're looking at some divergent series with non-negative terms, and our terms are greater than or equal to that divergent series terms. For n is less than n for some integer n, so n can be, just keeps on going. So basically we're saying our series will diverge if we're looking at another series that we know diverges, and our series terms are bigger than or equal to the divergent series terms. But that makes sense because our terms would be bigger. All right, this is called the direct comparison test. And I'm going to be like straight up that this is actually one of my least favorite ones, because you kind of have to be able to think ahead a few steps and be able to have a lot of well, it helps to have a lot of experience comparing things and knowing different series that converge or diverge. But we'll get through this, okay? All right, so if we are looking at some series as an example here, from 1 to infinity of 1 over 2n plus n. All right, I want to know if this converges or diverges. All right, does it converge or diverge? Well, I do know that 1 over 2 to the n plus n, it looks a whole lot like 1 over 2 to the n. So I'm going to just use my intuition about that. 1 over 2 to the n plus n. Let me compare it to 1 over 2 to the n and figure out what I can know. All right, basically, is this less than, equal to, or greater than this term over here for n's? I know that this is going to be from 1 to infinity positive, which is what I need. Or non-negative, I should say. But does this term, is it always going to be less than, greater than, or equal to this term? Well, 1 over 2 to the n, that series, it's kind of ugly, but there you go. That series is a geometric series, and I know it's going to converge because 1 over 2, the absolute value of that is less than 1. So I know this series converges, right? It's a geometric series. I know it converges. 1 over 2 to the n, if I add some number to the denominator, that's going to make 1 over this thing less than that one for all these n's, right? Because my denominator down here will be bigger than my denominator over here. So this is going to be actually less than 1 over 2 to the n the whole time. And I know that the series of this one converges. Okay, so what did I just figure out? I just figured out that this series will also converge because its terms are always going to be less than these terms, and I know that that series converges. So I can say by the direct comparison test, the sum from n equals 1 to infinity of 1 over 2 to the n plus n converges. Okay? Interesting. So let's take a look at the next one. Okay. So in this case, I'm looking at what looks to be a slightly more complicated situation. Okay. I have e to the negative n over n plus cosine squared of n. All right. First, are the terms going to be non-negative? And if I plug in n's going forward, yes, because this cosine is squared, it's always going to be positive, right? All right, so what do I know? I can do kind of a series of observations here. So I have e to the negative n over n plus cosine squared of n. All right, what do I know? What do I know? What do I know? Well, this is going to have to be less than or equal to. This is going to have to be less than or equal to e to the negative n over n, right? Because if I'm over here, am I just adding cosine squared? It's going to be adding some number to the denominator, making the denominator bigger than this one. So this guy has to be smaller than this one. Well, what does that mean? Well, if I'm dividing by n, and n is from 1 to infinity, I'm dividing by numbers. Well, this has to then be less than or equal to e to the negative n over 1, because with n down here, it'd be dividing by some number. So this is going to be smaller than this one. Smaller than or equal to that one. And what does that mean? This is going to be equal to e to the negative n. So I want to compare it to e to the negative n. What's going to happen to e to the negative n? That series. All right, that's going to be my direct comparison. So I'm going to say, I want to compare it now to the series e to the negative n. All right, wait, but e to the negative n, I know something about that. I could use the integral test to show this if I wanted to. Or I can say, hey, wait, this is 1 over e to the n. That is geometric. Right? That's going to be geometric. And it converges because 1 over e as my ratio, that's my r, is between -1 and 1. The absolute value of 1 over e is less than 1. So this is a geometric series that converges, okay? I just proved that the series of this converges, and I know that my series terms are less than that one. Therefore, by the direct comparison test, my series n equals 1 to infinity of e to the negative n over n plus cosine squared of n converges. And if you want to, you can strengthen this by saying the absolute value of r is less than 1, which is why my comparison series converges. All right? Let's look at a third one. Another kind of interesting example. So let's see, we have this series n over n squared minus cosine squared, okay? Well, here's what I'm thinking. Just looking at this, n over n squared, that looks a whole lot like, especially because this is going to be finite, the series will look a whole lot like n over n squared because cosine squared of n is going to stay between 0 and 1. This series will really behave a whole lot like n over n squared, but n over n squared is really a lot like 1 over n. So let me do another chain of reasoning over here. If I have n over n squared minus cosine squared of n, okay, n over n squared I know behaves like 1 over n, but I'm subtracting something from it. So it's making this denominator smaller, right? It's making this denominator smaller, which means it's going to be bigger than n over n squared. If it's bigger than that, bigger than n over n squared, well, n over n squared behaves like 1 over n. So my series here has to be bigger than 1 over n. And I know from my p-series stuff that the series from n equals 1 to infinity of 1 over n diverges because it's a p-series with p less than or equal to 1. All right, so I know my series diverges, but that my comparison series diverges, and I know that my terms have to be bigger than the terms over here, therefore mine diverges. So I now know that the series that I'm looking at diverges by the direct comparison test. Okay. Go ahead and try the next two. Oh, wait. Oh. Often, but not always, if you can tell here, we want to try to get series to compare to p-series. P-series are just so easy to work with because as soon as we see this, we can figure out that something converges. We compared to some geometric series up here, which is also useful, but oftentimes that comparison to p-series is just so nice because p-series, boom, 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 we can tell right away whether or not it's going to converge very, very quickly. All right, now pause the video, go ahead and try the practice problems below, A and B. Okay, here we go. Okay, so we are looking at two series, and we want to use the direct comparison test, right? 1 over n squared plus n plus 1, n is going from 1 to infinity, so this denominator is going to always be positive. Let's see, 1 over n squared plus n plus 1, what can I compare it to that will be bigger and smaller than? Well, the denominator is going to be getting bigger because I'm adding stuff. So as I'm adding stuff, this is going to be less than or equal to 1 over n squared, right? Okay, 1 over n squared. What do I know about that series? That series, from 1 to infinity of 1 over n squared, is a p-series. And it's going to converge because it is p-series with p being greater than 1. What does that mean? This is a great time to use these therefore symbols too. Therefore, by the direct comparison test. My series n equals 1 to infinity of 1 over n squared plus n plus 1 converges. Because my comparison series converges and my terms are less than or equal to the terms of that comparison series. They're less than because the denominator has to be bigger than this denominator. All right, let's go. Okay. We got one here, n squared over n cubed minus 3, right? All right. You might already know where this is going. We did one similar to this. Again, we gave a hint that it's nice to compare two p-series things. N squared over n cubed, that looks like it'll be a whole lot like the n squared over n cubed 1 over n kind of thing when we reduce it. Okay. So here's what we got to do. N squared over n cubed minus 3. It might be easy to say that, like, yeah, this denominator is going to be smaller, so it's going to be bigger than 1 over n. But we got to kind of get a way to show that. So let's think about it this way. We know that n cubed is greater than n cubed minus 3, right? Okay. If that is true, then I could also say this. If that's greater, if I'm taking n squared and I'm dividing it by n cubed and comparing it to n squared divided by n cubed minus 3, if n cubed minus 3 is the bigger thing, I'm dividing the same number by a bigger thing, then this, sorry, reverse that, back up, sorry. N cubed is bigger than n cubed minus 3. N cubed is the bigger thing. If I'm dividing the same number by a bigger thing over here, that means this side has to be less than that side, right? So our intuition is good. If you were sitting over here thinking, all right, n squared over n cubed looks like it's what's really happening here, which looks like it'll compare to 1 over n, you're right, but we need to show this, which is why I'm showing this up here. N cubed is greater than n cubed minus 3. That is true, so therefore n squared divided by n cubed is less than n squared divided by n cubed minus 3. All right. Now that we know that, though, we can make the comparison and say, okay, based off of that, I therefore know that 1 over n is less than n squared over n cubed minus 3. That's my original series, which is really saying, if we reverse it and put it in the order we have been looking at, that my series n squared over n cubed minus 3 is greater than my comparison series. My comparison series, I know, sums to, well, it diverges because it's the harmonic series. So I can say this diverges because p series with p is less than or equal to 1. All right, so therefore my series n equals 1 to infinity of n squared over n cubed minus 3 diverges by the direct comparison test. All right, because my series terms are going to be greater than 1 over n, which I know the series of those terms diverges, so my series has to diverge. All right, there's the direct comparison test. Last thing for today. We're going to look at now the limit comparison test, okay? So let's suppose that we have some terms, a sub n, which are greater than 0, and we know that b sub n is also greater than 0 for all n is greater than or equal to n, where n is some positive integer. So both of our terms are going to be greater than 0 if the limit of a sub n over b sub n, so just the terms, is c, and c is some thing between 0 and infinity, so positive, non-zero. Then the sum of both of those things, they either both converge or both diverge. If the limit of a sub n over b sub n, the terms, is 0 and b converges, then A series also converges. And if the limit as n approaches infinity of a sub n over b sub n approaches infinity, then the sum of b diverges, then the sum of a diverges. This is called the limit comparison test. But what does this essentially mean for us? Essentially, if we can take two terms that are parts of series, we can find the limit of a sub n over b sub n, and it's between 0 and infinity, so it's a limit that's not 0 and is positive. Then they either both converge or diverge. Why is this nice? Because if I can choose to compare, say, like b sub n as something I know converges or as that I know diverges, and that limit comes out to be between 0 and infinity, then I can conclude that my series converges also. Okay? These other ones are contingency things. If it comes out to be 0 and I know that b converges, the series of b converges, then the other one will converge. If I know if the series comes out to be infinity and b diverges, then the series of a will diverge. Just kind of backups for those other cases. Okay? Let's use the limit comparison test to do some things. All right. Okay. So, limit comparison test. Let me pull up my notes. Okay. So, I want the series from 1 to infinity of 2n plus 1 over n plus 1 squared, right? Well, just thinking ahead here, and this is where sort of projecting your mind a little bit, projecting your mind is useful. 2n dominates on top as n goes to infinity, because I'm going to be dealing with limits. And I get n squared on the bottom. Well, just as a thought on the side here, 2n over n squared really is a lot like 2 over n, right? So let me actually use 2 over n to compare to, because what do I know about 2 over n? I know that the sum of that series, n equals 1 to infinity, of 2 over n, it's going to be harmonic, will diverge. Right? I know it diverges. So let me do this. This is what I do then. I know that this diverges. Let me compare these terms to that one, and here's how that works. I'm going to say the limit as n approaches infinity of 2n plus 1 over n plus 1 squared divided by, actually this limit should apply to everything, 2 over n. Alright, it's a lot of stuff to write out. Now I just got to clean this limit up. Let me do that. So this will be the limit as n approaches infinity. Now dividing by a fraction, same thing as multiplying by the reciprocal. That'll almost always happen in this limit comparison test. So this will be 2n plus 1 over n plus 1 squared times n over 2. Alright. We could either at this point apply L'Hopital's rule or things like that if we wanted to. We could also just like take the time to expand stuff, which I will. So this will give me the limit as n approaches infinity of 2n squared plus n, multiplying n into the numerator there, over n squared plus 1 squared is going to give me, n plus 1 squared is going to be n squared plus 2n plus 1 times 2 down there. So continuing my limit, this is going to be the limit as n approaches infinity of 2n squared plus n over, distribute that 2n squared plus 4n plus 2. Aha, now I got my limits. I can say, oh, look at this. Cool. 2n squared is going to win up top. 2n squared is going to dominate underneath. So this is going to be equal to the limit as n approaches infinity of 2n squared over 2n squared, which is 1. All right, 1. What does that mean? 1 is between 0 and infinity. So that means that both of my sums will converge or diverge. Well, my sum I compared it to, my series I compared it to, diverges. Therefore, my series will also diverge. Then I can say, therefore, the series from n equals 1 to infinity of 2n plus 1 over n plus 1 squared diverges by the limit comparison test. Again, why? Because I compared it to a series I know diverges, and then after doing my limit comparison work, a sub n over b sub n, find the limit as n goes to infinity, came out to be between 0 and infinity. Therefore, since my comparison series diverged, my series diverges. Okay? One more, and then your practice. Okay? 1 over 2 to the n. Okay, 1 over 2 to the n minus 1, I mean. That looks a whole lot like 1 over 2 to the n. And what do I know about that series? The series as n equals 1 to infinity of 1 over 2 to the n. Looks like a good comparison. What do I know about this? Hey, that converges. Why does it converge? Because it's a geometric series, 1 over 2 to the n, and our ratio here, 1 over 2, what we'll multiply by each time, is between -1 and 1, so it converges. Let me compare it to that then. So here's my limit. My limit as n approaches infinity of 1 over 2 to the n minus 1 over 1 over 2 to the n. That's going to be equal to the limit as n approaches infinity of dividing by 1 over 2 to the n, same thing as multiplying by the reciprocal. This will give me 2 to the n over 2 to the n minus 1, right? Give me that limit. You could use different properties to reduce that, or simply kind of compare our limits here. 2 to the n, that's going to dominate on top. 2 to the n is going to dominate underneath, so this is going to be equal to the limit as n approaches infinity of 2 to the n over 2 to the n, which I know is 1. Okay, so I got a number between 0 and infinity. So what does that mean? I knew my comparison series converges. Therefore, my series from 1 to infinity of 1 over 2 to the n minus 1 also converges by the limit comparison test. All right. So I would like you to try the next two practice problems. Use the limit comparison test to determine whether the series converges or diverges. Give it a shot. All right, here we go. We want the series from 1 to infinity of 3n plus 2 over n minus 2, oh wow, where did that come from? 3n plus 2 over n cubed minus 2n. Alright, like we've done before, this comparison, if I'm just looking at the biggest terms as n goes to infinity, it looks like 3n over n cubed might be interesting to look at. And 3n over n cubed will be 3 over n squared. Interesting, because I know that the series of 3 over n squared, it's got a factor there, but 1 over n squared, that's a p series with a p greater than 1. So this is going to converge because it's a p series with p being greater than 1, which I know converges. Or you could use your integral test to check this. Integral test is great. All right? It converges. So what does that mean for us? Let's do my limit comparison now. My limit comparison then as n goes to infinity is going to be 3n plus 2 over n cubed minus 2n over, what did I decide? Oh, there it is. 3 over n squared. It's a lot of stuff, but we'll do it. This is going to be equal to the limit as n approaches infinity of 3n plus 2 over n cubed minus 2n times, multiply by the reciprocal, n squared over 3. This is going to give me the limit as n approaches infinity of, multiplying that in, 3n cubed plus 2n squared over, multiplying by 3, 3n cubed minus 6n. All right, looking pretty good. This limit doesn't look too bad. This limit is going to be equal to the limit as n approaches infinity of, all right, 3n cubed is going to dominate on top, 3n cubed is going to dominate underneath. So this is going to be equal to the limit as n approaches infinity of 3n cubed over 3n cubed. That's my n behavior model, which is going to be equal to, my limit of that is 1. Therefore, by the limit comparison test, the series n equals 1 to infinity of 3n plus 2 over n cubed minus 2n converges. Again, why? Because my comparison series converged. It was a p series with p greater than 1. Through my limit comparison, my limit came out to be between 0 and infinity. Therefore, by the limit comparison test, my series converges. All right. One more. Let's take a look. All right. N cubed minus 2n over n to the fourth. N cubed over n to the fourth. That's like 1 over n. And I know that my series 1 over n diverges. It's the harmonic series, right? All right, let me do my limit comparison to the harmonic series then. The limit as n approaches infinity of n cubed minus 2n over n to the fourth plus 3 over 1 over n is going to be the limit as n approaches infinity. Multiply by the reciprocal. N cubed minus 2n over n to the fourth plus 3 times n over 1. Distribute n, that's times 1, so that's not bad. Gives me n to the fourth minus 2n squared over n to the fourth plus 3. I know the limit then as n approaches infinity of, let's see, this n behavior model. Here will give us n to the fourth over n to the fourth will dominate there, which I know has a limit of 1. Therefore, by the limit comparison test, my initial series, the series n equals 1 to infinity of n cubed minus 2n over n to the fourth plus 3 diverges. Why? Because my comparison series was a harmonic series. It diverges, and after going through my limit comparison, I got a limit between 0 and infinity. Therefore, my initial series also diverges, just like the harmonic series. All right. As a side note, the limit comparison test is really nice because we can often use intuition about the limit to make the comparison. For example, are saying, hey, n cubed over n to the 4, that looks a whole lot like the harmonic series if we reduce those dominant terms. I really like the limit comparison test. It's easy to follow. But one thing to keep in mind is both of these tests take a lot of practice to get better and better at, especially as things get more complex, because you need to get quick at seeing what a series might compare to. All right. So we'll continue looking at these things over the next couple days, especially in the next lesson. All right, to get some more practice. For homework, please make sure you try those 5 problems. All right, and the 2 concepts that I have assigned. Have a wonderful day, everybody.